In this physics problem, we have a sphere with a ball sitting on top. The sphere has a radius a, and the ball is sliding down with an angle theta to the origin. And the goal of the problem is to find out at what angle on the sphere will the ball detach and fall to the ground. So first, on the top left, we're going to write our Lagrangian equation of motion. L equals T minus U. T being the kinetic energy of the ball, and U being the potential energy of the ball. And we know that U is equal to mgr cosine theta. We're also going to write our generic v vector in spherical coordinates, r dot r hat plus r theta dot theta hat plus z dot z hat. Actually, the z dot z hat does not matter in this situation, so we're going to cross that out. Now, our t, meaning the kinetic energy, is 1/2 mv squared. So in spherical, that means that t is equal to m over 2 times r dot squared plus r squared theta dot squared. Now, the Lagrangian identity says that del L del R is equal to d dt of del L del R dot. Del L del R minus d dt of del L del R dot is equal to 0, so we move that to the other side of the equation in this problem. Plus a lambda constant times del F del R, and that's our force of constraint. The force of constraint, F, is a function of R and theta. So in this case, F of R theta is equal to R minus A, which equals 0. So when you take the partial derivative of F with respect to R, you get, I'm going to box in the equation, L equals T minus U up there at the top left. So del F del R is equal to 1. So putting all of the pieces together, T minus U, we get the Lagrangian equation of motion, L, is equal to m over 2 times r dot squared plus r squared theta dot squared minus mg r cosine of theta. So now we can begin the calculus. The physics is done. We have put our Lagrangian equation of motion together. Now we need to use these identities to find out where on the sphere the ball will actually detach and fall to the ground. So, del L del R is the first piece that we need to find. And that is equal to mr theta dot squared plus mg cosine of theta. Next piece of the equation is finding d dt of del L del R dot. And that is equal to m r dot dot. And so, since we have both sides of the equation, we can write mr theta dot squared minus mg cosine theta minus mr dot dot plus lambda times 1 is equal to 0. Now we need to do the same process that we just did with r, but now take the derivatives with respect to theta. So, del L del theta is equal to d dt of del L del theta dot. plus del F del theta times lambda. So when you take all of these derivatives, you get mgr sine theta minus mr squared theta dot dot minus 2mr dot theta dot. R being constant in this situation. So this means that r dot is equal to r dot dot, which is equal to 0. And A equals R. So that means if you cancel out the m's on both sides, you can also cancel out an A. You can say that G over A sine theta is equal to theta dot dot. So we know that theta dot dot is equal to theta dot times del theta dot del theta. And the integral of theta dot with respect to theta dot is equal to G over A times the integral of sine theta with respect to theta. So taking those integrals and rearranging the equations, we get negative G over A cosine theta plus G over A is equal to theta dot squared over 2. And so theta dot equals 0 at t equals 0. Now using substitution, we know that lambda is equal to 0, which is also equal to mg times 3 cosine theta minus 2. Thus, the ball will detach from the sphere 2/3 of the way down. We know the potential energy of the ball as it's resting on the z-axis is E equals mga. So we know the velocity of this ball is going to be equal to the square root of 2gh. So v squared is equal to 2gh. That means that h is equal to a minus z. So v is equal to 2g times a minus z. We also have an r vector leading to the point where the ball will actually detach. That vector creates an angle theta with respect to the z-axis. Now, gravity is creating the force, mass times the acceleration of gravity on the ball. The force from the ball on the sphere is mg cosine theta. And the distance from the origin z to the ball itself is a minus z. So we're going to solve this problem using Newtonian mechanics. So m times dv dt is equal to mg plus r vector. This means that m times dv dt minus mg minus r vector is equal to 0. Now we know that 1/2 mv squared plus mg z is equal to total energy. That means that negative mv squared over a is equal to negative mg cosine of theta plus r. And from that we can say that negative mv squared over a is equal to negative mg times z over a plus r. That's because cosine theta in this problem is equal to z over a. So, rearranging that equation, we get r is equal to mg times z over a minus 2gm times a minus z all over a. Simplifying that, we get r is equal to mg over a, 3z minus 2a. So in the case that r is equal to 0, that means that 3z is equal to 2a. Solving the equation for z, we get 2/3 a. So that means that the ball will detach from the sphere 2/3 of the way down.